You see rectangles and squares literally every single day. They seem pretty simple, right? Kind of basic. But what if I told you that the official definition of a rectangle is hiding this beautiful piece of logical deduction? Today, we're going to unpack the surprising elegance of these fundamental shapes. So, let's dive in.
Just take a look at this. This is Frank Lloyd Wright's masterpiece, Falling Water. I mean, it's an icon of modern architecture, and if you really look at it, it's just this brilliant composition of rectangles. This is the perfect example of how these basic geometric shapes are, well, they're the building blocks of our entire world, from incredible art and architecture to just the everyday objects all around us.
All right, so let's start with the basics. We all know a rectangle when we see one, but what is it officially? We're about to unpack the surprisingly simple geometric definition of a shape we all think we know so well.
Now, if I ask you, hey, what's a rectangle? Most of us, myself included, would probably say something like, oh, it's a shape with 4 sides and 4 right angles. And you know what? You're not wrong. But in the world of geometry, that's not actually where the definition begins. And here it is, the official definition. A rectangle is simply a parallelogram that has a right angle. That's it. Just one, not 4. Now, that might seem a little weird, maybe even wrong, but this minimalism is the whole point, and it raises a pretty obvious question.
Exactly. How can just saying it has one 90-degree angle somehow guarantee that all 4 of them are going to be 90 degrees? Well, this is where the pure power of geometric logic comes into play. It's kind of like a domino effect that's built right into the definition itself.
Let's just walk through this logical chain together. First, like the slide says, a rectangle is a parallelogram. And being a parallelogram comes with a set of rules. Rule 1, consecutive angles, so the ones right next to each other, they always have to add up to 180 degrees. Rule 2, opposite angles are congruent, meaning they're identical. So if we just start by saying that one angle is 90 degrees, well, the angle right next to it must be 180 minus 90, which is also 90. And since the opposite angles have to be identical, the other 2 must also be 90. See? That one right angle knocks over all the other dominoes. So this solid logical foundation leads us to another really cool property, one that's only true for rectangles, not for all parallelograms. If you draw lines connecting the opposite corners, the diagonals, those 2 lines will be exactly the same length. But in geometry, we don't just say things are true, we have to prove it. So let's move on and see how this all builds. It's time to put on our detective hats and walk through a classic geometric proof. Now, I know, it might seem complicated at first, but it's really just a series of simple, logical steps. Okay, here's our mission, should we choose to accept it. We've got this rectangle, we'll call it MNPQ. We need to prove, without a shadow of a doubt, that the diagonal line from M to P is the exact same length as the diagonal line from N to Q. The secret here is to find 2 triangles that are kind of hiding inside the rectangle and prove they're identical. So let's focus on triangle NMQ and triangle PQM. The proof on the slide shows us how. First up, step 1, opposite sides. We already know side MN is congruent to side QP. That's just a basic property of all parallelograms. Okay, easy enough. Next, step 2, the shared side. Notice how both of those triangles share the side MQ? Well, a line is always congruent to itself. So, check. Finally, step 3, the right angle. We know for a fact that angle NMQ and angle PQM are both 90 degrees. So what have we got? We have a side, an angle, and another side that are the same for both triangles. Boom! That's SAS, or side-angle-side congruence, which you see in step 4. And because the triangles themselves are congruent, all their matching parts have to be congruent too. Which leads us to the grand conclusion in step 5. The diagonal MP must be congruent to the diagonal NQ. It's just a perfect chain of logic. And this is just a brilliant illustration of a core concept in geometry. A lot of the time, to prove something about a line or an angle, you have to look for a bigger shape it belongs to, like a triangle. If you can prove the triangles are the same, then you can prove their individual parts are the same. It is an incredibly powerful strategy. Now that we've really got a handle on the rectangle, let's look at its very famous, perfect cousin, the square. What is it that makes a square so special? So here's the thing. A square is a rectangle. It's a type of rectangle. It follows all the same rules. It's a parallelogram, it has 4 right angles, it has congruent diagonals, but it has one extra, very strict rule. all 4 of its sides must be equal in length. It's basically a rectangle that's also equilateral. You know, looking at them side by side really makes it click. They share almost every single property. They're both parallelograms, they both have 4 right angles, and equal diagonals. The only difference, the one thing that makes a square, is that bolded text on the right. All 4 sides are congruent. So remember this, every square is a rectangle, but not every rectangle is a square. Okay, now for the big payoff. That one defining feature of rectangles and squares, that all-important right angle, is the key that unlocks one of the most famous and useful tools in all of mathematics. I bet you've seen this before. A squared plus b squared equals c squared. This is the Pythagorean theorem. And here's the catch. It only works in triangles that have a right angle. It gives us this incredible way to find the length of a missing side if we just know the other two. So where do we find a right triangle? Well, just look back at our square or our rectangle. The second you draw a diagonal line, you perfectly split the shape into 2 right triangles. The 2 sides of the square become the legs A and B, and that diagonal you drew becomes the hypotenuse, C. And this is why it all matters. Because we know for a fact that a square has a right angle, we can use the Pythagorean theorem to calculate the exact length of its diagonal without ever needing a ruler. This principle is used every single day in construction, engineering, video game design, any field where you need to calculate distance and position. It all comes back to the simple, reliable properties of these shapes. So, the next time you see a window frame, or a sheet of paper, or your phone screen, maybe you won't just see a rectangle. Maybe you'll see this elegant system of rules just holding it all together. Thanks for joining me on this one.